Hey everyone, and welcome. Are you ready to become mathematical detectives today? We're going to dive right into Chapter 9, and honestly, this is where math gets really fun. We are finally taking those trigonometry concepts off the dusty chalkboard and bringing them out into the real physical world to solve some massive mysteries. So grab your mental magnifying glass because this explainer is all about the incredible, real-world applications of trigonometry. Now, I want you to just think about this for a second. Imagine trying to measure something truly massive, like Mount Everest. Or think about early astronomers trying to figure out the distance from the Earth to the planets and stars. They obviously didn't have a giant measuring tape that they could just stretch out into space. So how in the world did they do this seemingly impossible task? Well, they actually did it using the sheer superpower of right-angled triangles. The absolute secret to this impossible task is something called indirect measurement. You can think of trigonometry as your ultimate mathematical toolkit for measuring things you literally cannot reach. We don't actually need to climb to the very top of a towering building or a massive mountain to know exactly how tall it is. By just knowing a short distance we can measure down on the ground and a simple angle, we can unlock the heights of pretty much anything in the world. Okay, here is our roadmap for today to build up your conceptual mastery from scratch. We are going to cover 1. Trigonometry in real life. 2. Sights, elevations, and depressions. 3. Solving single triangle mysteries. 4. Conquering double triangle problems. 5. Mastering angles of depression. And finally, 6. Your heights and distances toolkit. All right, let's jump straight into Section 1, Trigonometry in Real Life. Let's see exactly how we can shrink these massive, unmeasurable structures right down onto our whiteboard. So the core concept we're dealing with here is called indirect measurement. Instead of dragging out a physical measuring tape, our new tools are simply going to be the angles we look at and the short, easy distances on the ground that we can actually walk across and measure. By using the geometry principle of similar figures and our standard trusty trigonometric ratios, we can calculate unreachable heights perfectly. It's literally like magic, but it's just math. Moving right along to Section 2, Sights, Elevations, and Depressions. These are the absolutely foundational observation tools you're going to need to build your right-angled triangles for every single problem. First, we really need to nail down the difference between our two main angles. Imagine a perfectly straight horizontal line coming right out from your eyes, parallel to the ground you're standing on. Now, if the object you are looking at is above that horizontal line, you have to tilt your head up, right? That upward tilt creates an angle of elevation. But if you're standing up on a high balcony looking down at something below that horizontal level, you lower your head. That downward tilt creates an angle of depression. So up for elevation, down for depression. Simple as that. Now, the invisible line connecting your eye straight to that object is called your line of sight. Just imagine shooting a laser beam directly from your eye up to the very top of a monument or down to a parked car on the street. That perfectly straight, invisible laser beam is your line of sight. And crucially, that line is going to form the hypotenuse of our imaginary triangle. Okay, let's get into the fun part. Section 3, Solving Single Triangle Mysteries. We're going to tackle example 3 from your textbook and apply these exact concepts. But wait, before we start crunching numbers, we need to know exactly which tool to pull from our tool belt. The absolute most important part of this entire chapter is knowing why we pick a specific trigonometric ratio. If you're trying to figure out a tall height and you know a distance flat along the ground, you need the ratio that connects the opposite side and the adjacent side. That is tangent. But if your problem involves, say, a ladder leaning against a wall or a stretched rope that forms a hypotenuse, and you need a height, well, then you'll use sine, because sine connects the opposite side directly to the hypotenuse. Let's actually verbalize one of these mysteries. Picture this in your head. An observer who is exactly 1.5 meters tall is standing 28.5 meters away from the base of a tall, smoking chimney. She looks up at the very top of the chimney, and her angle of elevation is exactly 45 degrees. Our mystery to solve? What is the total height of that chimney? Let's mentally draw it out together, because I promise you, correctly drawing the figure is like 90% of the battle here. Imagine our observer. We draw a straight horizontal line right from her eye level across to the chimney. Then we draw her line of sight angling up to the top, locking in that 45-degree angle. Finally, we drop a vertical line straight down for the chimney's height. Notice how the ground distance of 28.5 meters is exactly the same as that horizontal line coming from our eye. Boom, we've just built our right-angled triangle. So, looking at the triangle we just visualized, what do we know? We know the adjacent side, that horizontal distance from her eye to the chimney, is 28.5 meters. And we want to find the opposite side, the height of the triangle itself. So ask yourself, who connects the opposite and adjacent sides? That's right, tangent. Following these steps makes solving this an absolute breeze. We set up our equation, tan of 45 degrees equals our unknown opposite side divided by the adjacent side, which is 28.5. Now, since tan 45 perfectly equals 1, that means the opposite side is exactly 28.5 meters. But hold on, we aren't quite done yet. That's just the height of the triangle from her eye level up. The actual chimney goes all the way down to the ground, so we have to add the observer's own height of 1.5 meters back in. So 28.5 plus 1.5 gives us a total chimney height of exactly 30 meters. Mystery solved, case closed. Ready to level up? Section 4. Conquering double triangle problems. Let's look at example 7 and prove that these visually complex problems are really just two super easy triangles mashed together. Okay, imagine you were standing on a bridge, perfectly situated 3 meters above a flowing river. You look down at the riverbank on your left with an angle of depression of 30 degrees, and then you look down at the opposite bank on your right with an angle of 45 degrees. We need to find the entire width of the river across. Now, do not let the visual complexity of this scare you. Just imagine drawing a vertical line straight down from where you are standing on the bridge right into the water. We just split this one big, messy problem straight down the middle into two very simple right-angled triangles. By isolating each side, the math becomes incredibly easy. Let's look at the left triangle first. We know the opposite height is 3 meters, and we want the adjacent river width on that side. So we just use tangent 30 degrees to find that side, which we'll call AD. Then, jumping to the right triangle, we use tangent 45 degrees to find that side BD. Once we have the bottom widths of both of those individual triangles, what do? We simply add them together to calculate the total overall width of the river. You just break it down to build it back up. Section 5. Mastering angles of depression. Let's address the biggest trick in the book here. What exactly do we do when an angle is floating awkwardly outside of our triangle in a depression problem? Well, this is exactly where a classic rule from your earlier geometry days comes to the rescue. Alternate interior angles. Because your horizontal line of sight looking out from a high balcony is perfectly parallel to the flat ground way down below, the line of sight cutting between them acts as a transversal. This is a secret key that lets us perfectly flip that awkward outside angle of depression right down into the bottom corner of our triangle, turning it into a neat, tidy inside angle. It's that classic Z pattern at work. Seriously, drawing those parallel horizontal lines, it's going to be your absolute best friend here. Look at example 6. If you're looking down from a really tall multi-story building at the top and the bottom of a smaller 8-meter building across the street, you get two depression angles of 30 and 45 degrees. By using the alternate interior angles rule we just talked about, we instantly pop those outside angles down to the base of our imaginary triangles. It transforms a really confusing downward glance into a standard, easy-to-solve elevation problem. All right, we made it to section 6, your heights and distances toolkit. Let's wrap up everything we've learned into your ultimate real-world detective kit. I want you to remember this master summary whenever you face a problem. First, always clearly establish your line of sight. Second, draw your horizontal perfectly flat. Remember, if you have to look up, it's elevation. If you have to look down, it's depression. Third, if it is an angle of depression, use your alternate interior angles trick to drop it right inside your right angle triangle. And finally, pick the correct ratio. Usually, it's going to be tangent for heights and ground distances, or sine if a hypotenuse, like a ladder or a rope, is involved. And then you just solve the mystery. And there you have it. You have the complete conceptual mastery now. You don't just understand how to calculate these numbers, but you truly know why we set up these mathematical models in the first place. You literally hold the exact same mathematical power that early astronomers used to measure the stars. So go out there, tackle exercise 9.1 with absolute confidence. And hey, think about this. If a simple right-angled triangle can help you measure a massive chimney or a wide river, what's stopping you from calculating the size of the craters on the moon? I'll see you in the next explainer.
Hey everyone, welcome to this explainer. Today, we're doing something, well, kind of different. We aren't just reviewing math, we are literally cracking the code of the exam itself. Look, I've spent years as a veteran evaluator for the Karnataka SSLC board exams, specifically grading those subject code 81E papers. So I know exactly what the examiners are hunting for. And honestly, I know exactly where you're throwing away your hard-earned marks. Today, I'm pulling back the curtain on Chapter 9, Some Applications of Trigonometry. We're going to totally transform how you write your board exam.
Okay, so you know the formulas. You know what sine, cosine, and tangent mean, right? You've done the homework, you've memorized those textbook definitions, but here's the harsh reality. Knowing the formulas in your head and knowing how to actually extract full marks on that board answer booklet, yeah, those are two completely different games. The board doesn't just want the right final number. No way. They want to see a very specific, structured process. And if you don't play their game, well, you lose points.
So here is our playbook to game the system today. First, the SSLC exam blueprint. Second, high-yield question patterns. Third, inside the examiner's mind. Fourth, the minefield and mark traps. And finally, securing every half mark. Let's jump in.
All right, starting with part 1, the SSLC exam blueprint, focusing on those high-yield patterns. Here's a massive secret about the board exams. They are incredibly, almost predictably repetitive. Examiners are absolutely in love with specific templates, kind of like this classic 3-mark or 4-mark setup. We call this the building and tower elevation pattern. I mean, you've seen this setup 100 times in your prep, right? A tower on one side, a building on the other, and two angles of elevation crossing over, usually like 30 degrees and 60 degrees. This is an absolute favorite for the examiners. Why? Because they use this to test if you can handle two distinct right-angled triangles that share a common base. Master this specific geometry, and man, you've practically secured your 4 marks right there.
But you know, sometimes the board tries to throw you a curveball. Take a look at this one. This is the lighthouse and ships depression pattern. So here, the observer is up high, looking down at ships at 30 degrees and 45 degrees. The line of sight is horizontal, and the angles drop down. When students see the phrase angle of depression in the exam hall, they literally panic because the diagram feels, well, upside down. But I'm telling you right now, as someone who grades these papers, do not panic.
And this right here brilliantly illustrates exactly why you shouldn't panic. Look at them side by side. They are the exact same geometry. Seriously. Thanks to alternate interior angles, you know that classic Z-shape you learned about ages ago? Those angles of depression from the lighthouse just drop right down to become regular angles of elevation at the base. So whether the problem says elevation or depression, the board is just evaluating your ability to solve the exact same double right-angle triangle setup. It's a total visual illusion. Seriously, don't fall for it.
Moving on to part 2, inside the examiner's mind, where we'll do an autopsy of an answer.
Okay, I'm going to show you something most students never ever get to see. Boom! This is the official KSEAB marking scheme for that famous broken tree problem. Now, don't stress about reading every single bit of the math right now. Instead, I want you to anchor your eyes strictly to the right side of the screen, that marks allotted column. Look at exactly where the half marks live. You get half a mark just for establishing the 90-degree angle and substituting the squares. Another half mark for simply finding the square root of 100. We are literally handing out marks step by step just for the basic setup.
So, based on that official key answer we just analyzed, here are the 4 rigid steps you absolutely need to get full marks. 1. Draw the right angle figure. 2. Identify the correct trigonometric ratio. 3. Substitute your values. And 4. Provide the final answer with proper units. Think of this as your holy checklist. If you skip a step just to save a few seconds, you are actively choosing to throw away marks. Don't do it!
Just look at this official solution snippet. Notice how simply writing sine 30 degrees equals 20 over AB, and then immediately substituting the value 1/2 equals 20 over AB instantly secures a half mark. I mean, even if your final multiplication goes completely sideways under exam stress, you've already banked points just for communicating your setup to us. It's basically free marks.
Okay, part 3, the minefield. Let's talk about error prevention.
Now, I gotta be a little strict with you here. As an evaluator, it physically hurts me. I mean, it really does. To deduct marks from brilliant students all because of silly, entirely preventable errors. Contrast these two approaches right here. An amateur answer just slaps down the final calculated number. They look at the triangle, do the math in their head, and just write 10 on the paper. 0 marks for the process. A topper answer, though, they explicitly show the setup. They write out AB over BC equals tan theta before plugging in any numbers. Skipping that formula setup is a massive mark trap. If we evaluators can't see your logical flow, we literally cannot award you the step marks.
Here's a really high-yield memory aid for you to keep in your back pocket. The tangent function, it is the undisputed king of Chapter 9 board questions. Because we're almost always dealing with opposite heights, like buildings or towers, and adjacent distances along the ground, you need to know your tangent values cold. Start small, tan 30 is 1 over root 3. Move to the middle, tan 45 is a perfect 1. Get bigger, tan 60 is root 3. Burn this table into your brain, guys. It is the skeleton key for almost every single 4-mark question you're going to face.
Finally, Part 4, securing every half mark. Let's wrap this up.
We've seen the blueprint, we've peeked at the official marking scheme, and we've navigated the minefield. I'm going to hammer home this half-mark refrain one last time just to completely consolidate your advantage. Please, do not leave money on the table. Rule 1. Always draw the diagram. Even if it seems super simple, it grounds your whole answer. 2. State your formula first. Tell the examiner exactly what trig ratio you're using. 3. Show step-by-step substitution. And 4. Never ever forget your final units. If the tower height is in meters, write the M. Forgetting something as tiny as meters is just a tragic way to lose a half mark right at the finish line.
You now possess the evaluator's playbook. You know the exact visual patterns we use, you've seen the official grading keys where those precious half marks are born, and you know the silly traps to avoid. You aren't just guessing anymore, you are strategizing. So my final question to you is this: are you ready to walk straight into that exam hall and claim every single mark you deserve? Go dominate that math paper. Thanks for joining me on this explainer, and I'll catch you in the next one.